E kam një ide, në fakt 3-5-1-2.
I thought it was 3-2. No, okay. So I don't remember it. So this was 3-5.
1-2.
And what was the inverse?
Not inverse. We needed to find p in power of n multiplied with 1-0.
Oh, you're right. Okay, that's my mistake. So then let's multiply this with 1-0.
Now I have an idea about this, but I wanted to share with you first.
Sure. Go ahead.
I thought, what about we find the diagonalization of the matrix?
Of this one?
Yes, of this one, so that we can get, for example, A0, 0D.
What is A0?
At the end, after we have found the diagonalization, we will have A0, 0D in power of n.
That's correct. Okay, yes.
And then when we multiply it with 1-0, we will get A in power of n and D in power of n.
That is true. So here we have 3 minus lambda times 2 minus lambda. I agree with that. Minus 5, this would be equal to 0. So if it takes us less than a minute, let's find this. So here we get 6 minus 5 lambda plus lambda squared minus 5. This is equal to 0. Am I right? So let's check. This is 6 minus lambda plus lambda squared. Yes, this looks correct. We have lambda squared minus 5 lambda plus 1. This is equal to 0. What are the lambdas? Lambda 1, lambda 2, it's equal to minus b plus minus b squared minus 4ac. What is b squared? It's 25 minus 4 over 2. So this is equal to 5 over 2 plus minus square root of 21 divided by 2. 21 is 3 times 7, so we don't see anything new. But more or less, this is what we obtained. Then from here, we need to find the eigenvectors, because the eigenvalues, we found them. And okay. Yes. This was a good idea. So you are saying that we find eigenvalues, and then, so we have this matrix, then the diagonal matrix D is going to be equal to 5 over 2 plus square root of 221 over 2. This is approximately. Of course, we can use a calculator, we can find this perfectly. But 5 over 2, this is 2.5 plus, what is square root of 21?
4.58.
4.58, 4.6 divided by 2, this is 2.3 plus minus 2.3. So we get two values, which are 4.8 and 0.2. So the diagonal matrix is going to be 4.8,
0.20. When we multiply it with 1-0, we get only 4.8 to the power of n and 0.2 to the power of n, and we end the exercise. This was my idea.
No, this is a very good idea. And if we look at this, the expression here, we see that we have D is equal to P inverse, D is equal to P inverse A times P, right? What we can do is we can multiply here with P, right? And here we can multiply with P inverse, and here we get another P inverse. So we get here the identity matrix, here we get the identity matrix, and we find that P times D times P inverse, this is equal to matrix A. So then you are right. So if we write A to the power n, this is equal to P times D to the power n times P inverse. So is it what you mean, what you're meaning?
Yes, that's what I meant. I also found the P inverse and D. I also did it that way. And can I see the numbers? But they are too long. I did many calculations.
Don't worry. So which numbers you want to give, the P or for the D?
What? For the P, for the P.
What, okay, so what is the matrix P?
The matrix P was 1 over 2 minus the square root of 21 over 2. 1 over 2 plus the square root of 21 over 2, 1, 1.
Where do I write that number here?
What?
What number should I write here?
I got 1/2 plus square root of 21/2.
Okay.
1, 1.
1, 1. Okay. So this is invertible because the determinant of this matrix is different from 0 because this column is not linearly dependent to this other column. So we are good at it. So at least we know that just by looking at this P that we have given to us, we can say that the P inverse exists. Okay, exists.
Yes, at first I did an approximation to get rid of the root, and I got P. Can I say the values?
Yes.
I got P equal to minus 1.8, 2.8, 1, 1.
So this was for P?
Yes, approximately, because they were floating numbers with a very large fractional part.
That's fine, that's okay. So the determinant, this is, but the determinant of this one is then what? This is, looks like, no, it's 4.8, right? 4.6, minus 4.6. So the determinant here, it is 4.6 or minus 4.6. That's what I see from here. Approximately, of course. And then, okay, what you proposed, it was a good choice. But then, what is interesting is that if we have here P and d to the power n, we get here 4.8 to the power n times 0 times 0 times 0.2 times P inverse. Now, I can erase this because I was just trying to look what the numbers look like. Okay, so we found the lambda, but this is times P inverse. And when we look at this expression, you are going to be an engineer. What do you observe here? Now, when we say what we observe here, we assume what happens if n is 100. Okay, this is what you should be caring about. You should be caring about the most dangerous aspect of the numbers. What is 4.8 to the power 100? Where does this go? So this diverges to infinity. Okay, so it's a problem. So of course, 4.8 to the power 1, we have no trouble. 4.8 squared is fine. Okay, we're not talking about this domain, but we know that n is a number that increases, and then this is also to the power n. Do we have any problem here? What is 0.2 to the power n? Where does this go if n goes to infinity?
It approaches 0.
That is true. So which means that for us, we don't have any issue with the 0.2 showing up in here, but we could have an issue with this 4.8 to the power n, which means that we cannot go too far into calculating this matrix A to the power n times this vector. We could, but we don't have enough space in a piece of paper to write very large numbers. Okay, so we can run with using approximately a relatively small number of them. Now, we started this discussion because this matrix, it was a unimodular matrix, so let's see what is the first result if we multiply 1 with the vector 1, 0. We have here, this is equal to 3, and this is equal to 1, right? Is this correct? This is 3 and 1. And here, we multiply. What if we multiply the 3, 1 with the same matrix? What we get here, it's 9 plus 5 is 14. Then we have 3 plus 2 is equal to 5. Then we multiply again, we get 3 times 14. So it looks like we are rotating these vectors. And this is 3 times 14, it is
67.
42 plus 25, this is 67. You said 67? Okay, I missed it. So this, then here we have 14.
24.
24, yes, 24. And then we continue like this. Of course, the numbers will blow up very soon. So here we have 67 times 3. This is 201. 201 plus 100, 301 plus 20, 321. 321. And then we get here 67 plus 48. This is 115. 115. So it goes on like this, but it looks like these numbers will very soon approach to relatively large values. And what would be interesting for you to notice, to try to draw, would be where is 3, 1? 1, 2, 3, 1. So the tangent here, the tangent of this angle theta is equal to 1 over 3, right? The tangent here, it is 5 over 14. So it looks like it's going to be, I'm not sure which one is larger. If we just what is the common denominator here? It looks like this is going to be 14 and this is going to be 15. This is larger, okay? So you can check, it looks like, is this vector going to decrease this angle or increase this angle? To me, it looks like at first stage, it's going to increase the angle. This is 1 over 3. Wait a second. Yeah, this is. So this is, again, smaller than 1 over 3. So this looks like.
I think it's going to be bigger.
You mean the slope? I don't know. You think about this problem, okay? Because it takes some time. But since I noticed that this matrix here, it was a unimodular matrix, we could have seen something special, but we didn't see this. A couple of times we came up with some random unimodular matrices, which allowed us to rotate the given vector and keeping it within some bounded region, okay, in the R² space. Okay, so we can, this was the exercise we were just talking before a while. We're going to talk now regarding this representation. We're going to write this one in a more formal way in the next session. But for now, let's continue with another example. So I'm going to leave this one for a while here. Ray, wait a second. Okay, let's give another break.